Right now, at this exact moment, there are regions of the universe so far away from you that nothing can ever reach them. Not a rocket, not a radio signal, not light itself, not even the concept of, hello, these places exist. They're real. They have galaxies and stars and possibly planets, and possibly beings staring up at their own skies, wondering the same questions you're about to wonder. And here's the part that should make your brain stutter for a second. They are moving away from you faster than the speed of light. Right now, as you watch this video, the universe is tearing itself apart at speeds that shatter the most fundamental rule of physics, the rule that says nothing travels faster than light. Except here's the devastating twist. The universe isn't breaking that rule. It's doing something far more disturbing. It's found a loophole so profound that it doesn't just challenge how we understand space. It challenges whether cause and effect, the very backbone of reality itself, can survive. Think about what cause and effect means for a moment. Every single thing you've ever experienced runs on it. You drop a glass, it shatters. You flip a switch, the light comes on. You were born because your parents met, because their parents met, because somewhere back in time, a chain of causes stretched back to the beginning of everything. Cause and effect is not just a law of physics, it's the architecture of existence. It's what makes before and after meaningful. It's what makes you meaningful, because you are, right now, the effect of 4 billion years of unbroken causation. But what if the universe expanded faster than that chain could hold together? What if there were places, real existing places, where cause and effect simply doesn't reach? What you're about to discover over the next 3.5 hours is not science fiction. Every concept we're going to explore is rooted in peer-reviewed physics, published experiments, and the work of some of the most brilliant minds in human history. What you're going to feel by the end of this video is something that very few people on Earth ever feel. The specific, vertiginous sensation of understanding that the universe is not only stranger than you imagined, but stranger than you are capable of imagining before today. And that changes you permanently. Before we go further, if you haven't subscribed yet, right now is actually the perfect moment, because this video is the first in a series that's going to take you deeper into these ideas than anything you've probably seen on YouTube. Hit that subscribe button. Hit the bell so you don't miss what's coming. And I want to ask you something genuinely. Drop a comment right now. What country are you watching from? And what time is it where you are? I ask this every video, and the answers never stop astonishing me. People watch these videos at 2 a.m. in Lagos, at noon in Seoul, at sunrise in Buenos Aires. You are part of a global mind reaching for the same questions at the same moment. Tell me where you are. Let's see how far this reaches. Now, let's start with the most shocking revelation first, so that everything that follows lands with the weight it deserves. In 1998, not ancient history, 1998, the year Titanic won the Oscar, two teams of astronomers were racing each other to measure how fast the universe's expansion was slowing down. They were not looking for acceleration. They were measuring deceleration. They knew, everyone knew, that the expansion from the Big Bang had to be slowing the way a ball thrown upward slows as gravity pulls it back. Saul Perlmutter led one team. Brian Schmidt and Adam Rees led the other. These were serious, rigorously trained scientists doing serious, careful science. And what they found, independently, checking each other's math, rechecking their instruments, suspecting their own equipment of malfunctioning, was that the universe was not slowing down. It was speeding up. The expansion of space was accelerating, and not gently. It was racing toward velocities that would, in the deep future, push every galaxy outside our local cluster, beyond the horizon of what we can ever observe, communicate with, or affect. They won the Nobel Prize in Physics in 2011 for this discovery. And to this day, the thing driving that acceleration, what physicists call dark energy, remains one of the most profound unsolved mysteries in all of science. But here's what most people don't know about that discovery. What most people never connect. If the universe is accelerating its expansion, it's not just pushing galaxies away from us. It's pulling them across a boundary called the cosmological event horizon. And once something crosses that boundary, the light it emits can never reach us again. That because the light is slow. Not because space is too thick, but because the space between us and that light is expanding faster than the light can cross it. The light runs, and the finish line moves away from it forever. That boundary isn't just a limit on what we can see. It's a limit on what can ever cause anything in our observable universe. And that is where today's question becomes genuinely terrifying, genuinely beautiful, and genuinely world-altering. What does it mean for the nature of causality when the universe itself can expand faster than cause and effect can travel? Stay with me. Because we haven't even gotten to the part that blows your mind yet, that's coming. And it's going to reframe every single thing I just told you. But first, we need to establish something. We need to understand what the speed of light actually means, not as a speed limit for objects, but as a speed limit for information. Because once you understand that, you'll understand why an expanding universe doesn't just limit what we can see. It might be literally ripping the fabric of cause and effect apart, right now, in real time, while you sit here watching this video. Let me ask you something that sounds simple, but isn't. Why can't anything travel faster than light? Most people, if you ask them, will say something like, because Einstein said so, or because it would take infinite energy. And those answers are correct, technically. But they're the surface of something much deeper, something that connects directly to why faster than light expansion threatens the very concept of cause and effect. Here's the real answer. And it's one of those answers that, once you hear it, you'll never unsee it. The speed of light is not fundamentally a speed limit for objects. It's a speed limit for information, for causation. Think of it like this, and this is our first analogy, so hold on to it. Think of it like ripples in a pond. When you drop a stone in water, the ripple moves outward from where the stone hit. If you're standing at the edge of the pond, you know the stone dropped the moment the ripple reaches you. The ripple is the information that the stone dropped. It's also the cause of your knowing. Now imagine the pond is so enormous that the ripple, moving at a fixed maximum speed, takes years to reach you. Until it does, you have absolutely no idea whether the stone was dropped or not. You cannot respond to it. You cannot be caused by it. You are, for all practical and physical purposes, disconnected from that event. That's what the speed of light does for reality. Albert Einstein, in 1905, working as a patent clerk in Bern, Switzerland, a 26-year-old who had failed to get an academic job, published a paper that contained one of the most philosophically devastating ideas in human history. He called it the special theory of relativity. And buried inside the mathematics was a discovery that transcended physics and became something closer to a statement about the nature of time itself. Causally connected events, events where one causes the other, must be connected by something moving at or below the speed of light. If you are here and I am there, and the distance between us can only be crossed in 10 seconds at the speed of light, then nothing I do right now can cause anything in your experience for at least 10 seconds. The universe enforces this, not as a suggestion, not as a guideline, as an absolute, ironclad, no exception structural feature of space-time itself. Physicists even have a name for this structure. They call it the light cone. Imagine standing in the present moment, and from you, a cone of light expands forward in time. Everything inside that cone is your future, the realm of things you can potentially affect. Behind you, another cone opens backward in time. Everything inside is your past, the realm of things that could potentially have caused you. The boundary of those cones is drawn by the speed of light. Anything outside the cones, above, below, to the sides in spacetime is called space-like separated. And space-like separated events have a profound, strange, universe-altering property. They cannot cause each other. Physicists say they are causally disconnected. One cannot affect the other. One cannot send information to the other. They exist in a relationship that has no before or after, depending on who's measuring them. They can appear simultaneous, or one can appear to precede the other, and both observers would be equally right. Time ordering itself breaks down for causally disconnected events. Now here's where we turn the key. If the expansion of space pushes two regions apart faster than light can cross between them, those regions become space-like separated permanently, causally disconnected forever. One cannot affect the other. One cannot send information to the other. And if cause and effect require the ability to send information, then in a universe that expands faster than light, there are regions of reality that are causally isolated from each other, sealed off, not by walls, not by distance, but by the expansion of space itself. Now you might be thinking, okay, that sounds like it just means we can't see some galaxies. So what? And I love that you're thinking that, because it means you're already engaging with this at the right level. And I'm about to show you why the consequences are so much more disturbing than just losing some galaxies from view. Let me introduce you to a physicist named John Wheeler. Wheeler worked at Princeton alongside Einstein, and he coined two of the most important phrases in all of 20th century physics: black hole and it from bit. The idea that information is the most fundamental substance in the universe, not matter, not energy, information. Wheeler believed, and many physicists since have built entire careers on this idea, that the universe is, at its most basic level, informational. That physical reality emerges from the processing and transmission of information. If Wheeler is right, and the evidence is increasingly suggesting he was onto something profound, then a universe that expands faster than information can travel is not just a cosmological curiosity. It's a universe that is tearing the informational fabric of reality, creating regions where reality, in some genuinely fundamental sense, becomes unconnected, causally orphaned. Here's what will blow your mind. Mind-blown moment number one. Right now, as you sit there is a sphere around you, centered on you, called your observable universe. It's about 93 billion light years in diameter. Everything inside that sphere has, at some point in the history of the universe, been in causal contact with you. But this is changing. Because of dark energy's acceleration, that sphere is effectively shrinking in terms of what you can exchange information with in the future. Galaxies are being permanently exiled from your causal reach. Not hypothetically, not eventually, right now. As I speak, the universe is editing its own connectivity, deleting causal links between places that were once connected. And here's the cliffhanger that should follow you into our next section. If the universe can delete causal connections between distant galaxies, if it can sever the link between cause and effect on cosmic scales, then what does that say about the nature of causality itself? Is causality a fundamental feature of reality? Or is it a local phenomenon, something that only exists within the limited bubble where expansion hasn't yet severed the threads? Is cause and effect as fundamental as we thought? Or is it just a regional feature, a local rule, something that works in our neighborhood of the universe the way local traffic laws work, real and binding here, but irrelevant once you cross the county line? That question is about to get a lot heavier, because to answer it properly, we need to talk about what the universe looked like at the very beginning, during a period when the expansion wasn't just faster than cause and effect. It was incomprehensibly faster, a period that has left scars on the sky that we can still observe today, a period that some physicists believe created the causal structure of everything that came after. We need to talk about inflation. Okay, I need you to brace yourself for this section, because we're about to talk about an event in the history of the universe that makes every other event, every war, Every extinction, every supernova, every galaxy collision looked like a quiet Tuesday afternoon. We're talking about cosmic inflation. And what happened during inflation makes our current accelerating expansion look like a leisurely bicycle ride by comparison. Here's the setup. The Big Bang happened approximately 13.8 billion years ago. And in the very first moments after it, not minutes, not seconds, not milliseconds, we're talking about a time interval so small it makes a billionth of a second look like geological time. The universe underwent an expansion that defies human intuition so completely that I genuinely don't know if I can convey it with words. But I'm going to try. In approximately 10 to the negative 32 seconds, that's 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000ɔ In the language of everyday experience, that's a factor of 100 million billion. In the language of everyday experience, if an atom expanded by the same factor during inflation, it would become larger than the observable universe today. This is not a metaphor. This is not a poetic exaggeration. This is what the mathematics demands, and what the observations increasingly confirm. And here's what's important for our story today. During this inflationary period, every single point in the universe was expanding away from every other point faster than the speed of light. Incomprehensibly faster. Light couldn't keep up. Information couldn't keep up. Cause and effect couldn't keep up. The universe was, for that extraordinary fraction of a second, in a state where causality was not merely stretched, it was atomized, shredded. The coherent web of cause and effect that we rely on for reality simply did not exist on scales larger than an unimaginably tiny distance. Now, who figured this out and how? Because this is one of the great detective stories in the history of science. In 1980, a young physicist named Alan Guth was working at Stanford and wrestling with a problem that had been bothering cosmologists for years, several of them actually. 3 specific problems that seemed completely unrelated, but were all pointing at the same something is missing gap in the standard Big Bang model. The first was the flatness problem. The universe, we can measure, is almost perfectly geometrically flat, like a flat sheet of paper, rather than a sphere or a saddle. For it to be this flat today, it would have had to be fine-tuned to an absurd, almost impossible degree of flatness at the beginning. The slightest deviation, 1 part in 10 to the 60, and the universe would have either collapsed back on itself or expanded so fast that no structure could ever form. This level of fine-tuning struck physicists as deeply suspicious. Nature doesn't usually set up its initial conditions with that kind of precision without a reason. The second was the horizon problem. When we look at opposite ends of the observable universe, regions so far apart that light hasn't had time to travel between them since the Big Bang, we find that they have almost identical temperatures, down to a tiny fraction of a degree. But if these regions were never in causal contact, if light never had time to cross from one to the other, how did they agree on the same temperature? How did they coordinate? They couldn't have sent signals to each other. They couldn't have equilibrated in the normal thermodynamic sense. And yet they're identical. The third was the magnetic monopole problem. The physics of the early universe predicted that exotic particles called magnetic monopoles should have been produced in vast quantities. Yet we've never found a single one. 3 unsolved problems. 3 different symptoms. And Alan Guth, in what he later described as the most exciting night of his scientific life, he wrote spectacular realization in his notebook at 11:56 p.m. on December 6, 1979, solved all 3 simultaneously. The solution: the universe underwent a period of exponential inflation, Think of it like this, our second analogy. Think of it like a wrinkled balloon. Imagine the early universe as a tiny, wrinkled, lumpy balloon. Now inflate it by a factor of 100 million billion billion. The wrinkles? Gone. The surface becomes so large relative to any feature that it looks perfectly flat in every direction you can see. The opposite ends of the balloon? They were in contact before inflation stretched them apart. So of course they have the same temperature. They agreed before they were separated. The magnetic monopoles? Diluted across a volume so vast that having even one in the observable universe becomes statistically nearly impossible. One mechanism, three solutions. This is the signature of a discovery that's touching something true. But here's the part that connects directly to our central question today, and it's the part that should make your thoughts go quiet for a second. Inflation didn't just separate distant regions. It took quantum fluctuations, the tiny, probabilistic wobbles of quantum mechanics that exist at the smallest possible scales, and stretched them across the sky. It took things that were causally connected at quantum scales, and snap, stretched them to cosmic scales. Those quantum fluctuations became the seeds of galaxies. The slight variations in temperature we can measure in the cosmic microwave background radiation, the faint afterglow of the Big Bang that we can observe today with telescopes like the Planck satellite. Those variations are the stretched echoes of quantum events that happened when the entire observable universe was smaller than a proton. You are made of atoms. Those atoms formed in stars. Those stars formed from gas clouds. Those gas clouds formed from density variations in the early universe. And those density variations are the stretched fingerprints of quantum events that occurred before causality was even established. You are, in a very real sense, the long-term consequence of events that happened before cause and effect existed. Let that sit for a moment. Now here's what's going to blow the roof off in the next section. Because so far, we've been treating inflation as a solved problem, an elegant solution to cosmological puzzles. But the truth is far stranger. When physicists actually work through the mathematics of inflation, they find that it doesn't stop. It doesn't just explain the universe we see. It generates an infinite number of universes we can never see. And each of them has its own causal structure. Each of them has its own laws of physics. And some of them might have cause and effect running in the opposite direction. Let's go there. What if I told you that inflation, once started, essentially cannot stop? Not, it's hard to stop. Not, it tends to keep going. I mean, the mathematics of inflation, worked out carefully, shows that it will continue in some regions of space forever. Not just for a long time. Forever. This is called eternal inflation, and it's one of the most controversial, most profound, and most consequential ideas in modern cosmology. It was developed primarily by the physicist Andrei Lind, who was working in Moscow in the 1980s and has spent decades at Stanford refining these ideas. Lind is one of the intellectual giants of our era, and what he found when he worked through the dynamics of inflation is something that permanently changed how physicists think about the universe. Here's how eternal inflation works. Imagine that inflation is driven by a field of energy. Physicists call it the inflaton field, that's permeating space and slowly rolling downhill toward a lower energy state, like a ball rolling down a bumpy landscape. When the field reaches the bottom of its energy landscape, inflation stops, and the energy converts into the matter and radiation of a Big Bang, our Big Bang, for instance. But in quantum mechanics, fields don't roll smoothly. They have random quantum jumps. And in some regions, those quantum jumps push the field back uphill faster than it's rolling down. In those regions, inflation continues. And because inflation makes space expand exponentially, the inflationary regions grow so much faster than the non-inflationary regions that, statistically, inflation always dominates. New patches of universe are being created faster than inflation is stopping anywhere. The result is an eternal, ever-expanding foam of spacetime, with bubble universes, pocket universes, nucleating within it wherever inflation locally ends. Each bubble is causally isolated from every other bubble, not just separated by vast distances, fundamentally causally disconnected. The expansion between bubbles is faster than light, permanently. No information, no signal, no cause can cross from one bubble to another. Think of it like this, our third analogy. Think of it like an infinite ocean of bread dough, baking. Within the dough, bubbles of air form. Each bubble is a universe. The dough between the bubbles keeps rising, keeps expanding, keeps pushing the bubbles apart at speeds no signal could ever cross. The bubbles can never communicate. They can never affect each other. They are, in the most complete sense possible, causally orphaned from each other. Each bubble universe is a causally closed system. And here's where it gets genuinely strange, in a way that connects directly to our central question. Each of these bubble universes can have different physical constants, different strengths of gravity, different masses for the electron, different values for the cosmological constant, the parameter that controls how fast space expands. Some might have no stable atoms. Some might have gravity so strong that matter immediately collapses. And some, this is the connection, some might have physical constants that give rise to a different relationship between space and time, a different maximum speed of information transfer, a different structure of the light cone, a different causal architecture. In other words, some bubble universes might have cause and effect running differently, not metaphorically, physically differently. In 1949, Kurt Gödel, the same Gödel who proved that mathematics contains truths that cannot be proven, found an exact solution to Einstein's field equations, describing a rotating universe in which time is circular. You could, in principle, travel through that universe and arrive at your own past. Cause and effect would be cyclical. Your effect could become your own cause. Gödel was deeply disturbed by this discovery. Einstein, who had become a close friend during their years together at the Institute for Advanced Study in Princeton, found it deeply unsettling. It implied that time, and therefore causality, was not a fundamental feature of the universe, but a contingent one that depended on the geometry of space-time in your particular region. Some of the bubble universes in Lind's eternal inflation landscape might have geometries like Gödel's rotating universe. Some might have closed time-like curves, paths through space-time that loop back to their own past. In those universes, the question what caused what might not have a well-defined answer. Causality in those universes is not broken, it's simply structured differently. The web of cause and effect, instead of being a linear chain pointing from past to future, might be a loop, or a network with no defined direction, or something else entirely that we don't yet have the mathematics to describe. Now, you might be thinking, this is fascinating, but what does it have to do with our universe? Are we just speculating about places we can never reach? Fair question. Excellent question, actually. And the answer is, these ideas are not just speculation, because eternal inflation has made predictions that we can test. And some of those predictions have been confirmed. If bubble universes nucleate within the inflationary foam, and if two bubble universes were to collide, which is theoretically possible under certain conditions, the collision would leave a distinctive imprint in the cosmic microwave background radiation, a circular ring slightly hotter or cooler than the surrounding region. Physicists Stephen Feeney, Matthew Johnson, Haranya Paris, and Andrew Ponson searched the Planck satellite data for exactly these signatures in 2011 and found 4 candidate signals. The evidence is not definitive, but it's not nothing. We may be looking at the bruise left by a collision between our universe and another causally isolated bubble, another reality that can never communicate with us, that we can never affect, and that can never affect us, but that once, long ago, in the earliest moments of our universe's existence, rushed against us in the inflationary foam and left a mark in the sky. If that's true, if those circular anomalies in the microwave background are real collision signatures, then we have observational evidence for a realm beyond our causal horizon. Evidence that causality itself has edges, walls, places where the chain of cause and effect terminates, not because nothing is there, but because the architecture of expansion has made those regions forever unreachable. But everything we've talked about so far has been about regions outside our observable universe. What about inside it? What if faster-than-light expansion isn't just a feature of cosmic scales? What if something similar happens right here, in the quantum fabric of space-time? What if there are events happening right now that violate the causal structure we've been describing, not by breaking the rules, but by exploiting something in quantum mechanics that Einstein called spooky action at a distance? What if quantum entanglement is a clue that causality isn't what we think it is? In 1935, Albert Einstein co-authored a paper with Boris Podolsky and Nathan Rosen that was intended to be a devastating critique of quantum mechanics. The paper argued that quantum mechanics was incomplete, that it was missing something, that it was, in Einstein's word, spooky. The specific spookiness he was pointing at was something that would come to be called quantum entanglement. And Einstein was convinced it couldn't be real, that it violated everything he knew about causality and locality, the twin pillars of physical reality. He was right that it was spooky. He was wrong that it couldn't be real. Here's what quantum entanglement actually is, stripped of mysticism and stated precisely. When two particles interact in certain ways, they can enter a shared quantum state. Their properties become correlated in a way that cannot be explained by any information that was stored locally in each particle before they were separated. When you measure one particle, say, measuring its spin and finding it up, the other particle's spin instantaneously becomes down, no matter how far away it is. Not eventually becomes down after a signal travels between them, instantaneously. In 1964, physicist John Bell, working quietly at CERN on what he thought might be a minor mathematical footnote, derived what are now called Bell's inequalities. These are mathematical bounds on how correlated two particles can be if their behavior is explained by local hidden variables, pre-existing properties that were set when the particles last interacted. If those bounds are violated in experiments, it means the correlations cannot be explained by any local hidden variable theory. It means the universe is, in Bell's precise technical sense, non-local. And the experiments? In 1972, John Clauser and Stuart Friedman performed the first Bell test. The results: Bell's inequalities were violated. The universe is non-local. In 1982, Alain Aspect's team in Paris performed a far more rigorous version, closing several loopholes, and got the same result. The violations were real. And in 2022-2022, 3 years ago, Alain Aspect, John Clauser, and Anton Zeilinger were awarded the Nobel Prize in Physics for this body of work, confirming that quantum non-locality is one of the established facts of physics. The universe is non-local. The correlations between entangled particles are real. They're instantaneous across arbitrarily large distances, and they cannot be explained by any model where each particle carries local hidden information. Now here's the tension. The tension that should be keeping physicists up at night, and in some cases is. If those correlations are instantaneous, if measuring one particle instantly determines the state of its partner light years away, isn't that faster than light? Isn't that violating the causal structure we've been talking about? Isn't that a way of sending information faster than causality allows? And here's the answer that is simultaneously reassuring and deeply unsatisfying. You can't use entanglement to send information. When you measure your particle and get up, you have no control over which result you'll get. The result is random. Your partner, measuring their particle light years away, also gets a random result. Only when you compare notes, a process that requires a classical signal traveling at or below the speed of light, do you discover the correlation. The correlation is there. The correlation is instantaneous. But you can't exploit it to send a message. The universe has arranged itself in precisely the right way that quantum non-locality exists, but cannot be used to violate causality. Think of it like this, our fourth analogy. Think of it like a pair of gloves. You take a pair of gloves, separate them without looking, put one in a box, and ship it to the other side of the world. The moment you open your box and see a left glove, you instantly know the other box contains a right glove. That correlation is real and instantaneous. But no information traveled between the boxes. The information was established when the gloves were paired. The trouble with quantum entanglement is that it's not like gloves. There are no hidden variables, no preset properties. No, the gloves were already left and right before you opened the box. The particles genuinely don't have definite spins until measured. And yet, the correlation exists. And yet, you can't use it to send information faster than light. What this means is that the universe has two levels. At the classical level, the level of objects, signals, causes, and effects, causality is preserved. Information cannot travel faster than light. But at the quantum level, the level of correlations and entanglement, the universe is secretly non-local, connected across distances in ways that don't respect the causal architecture of space-time. These quantum connections can't be used to violate causality, but they suggest that underneath the classical world we experience, underneath the world of causes and effects, there is a quantum substrate that is not structured by causality in the same way. Physicist David Bohm, who spent decades developing what's called the pilot wave interpretation of quantum mechanics, argued that this quantum non-locality pointed toward what he called the implicate order, a deeper level of reality in which everything is fundamentally connected, and the separate, causally structured world we experience is an explicate order that unfolds from this deeper unity. The physicist John Bell, who derived the inequalities that proved non-locality, was deeply sympathetic to Bohm's view. And here's what makes this directly relevant to our universe's expansion. If there is a quantum substrate beneath causality, if the causal structure of spacetime is something that emerges from a deeper, more connected reality, then an expanding universe that tears causality apart at cosmic scales might not be destroying something fundamental. It might be revealing the seams, showing us the places where the classical, causal surface of reality is thin, where the quantum substrate underneath shows through. The universe expanding faster than cause and effect might be, literally, peeling back the causal layer and exposing what's underneath. What's underneath causality? That's the question that's going to drive the next section, and it's going to take us somewhere genuinely unexpected, to the idea that time itself, the thing that makes cause come before effect, might not be fundamental, might not be real, in the deepest sense at all. What if I told you that one of the most respected theoretical physicists alive today, someone whose technical work is cited by everyone in the field, believes that time does not exist? Not that time is weird, or counterintuitive, or hard to define. That it does not exist as a fundamental feature of reality. Carlo Rovelli is an Italian physicist who helped develop loop quantum gravity, one of the leading candidates for a quantum theory of gravity. He's written best-selling books that have sold millions of copies around the world. And his professional, technical, peer-reviewed position, not a popular science speculation, but a consequence of working through the mathematics of quantum gravity, is that time is not a fundamental ingredient of the universe. It's an emergent phenomenon, something that arises from the statistical behavior of a large number of particles, the way that temperature arises from the average kinetic energy of molecules. Temperature is real. You can feel it. But there's no fundamental particle of temperature at the quantum level. It emerges. And Rovelli argues that time is the same. This matters enormously for our question today. Because if time is not fundamental, if it's emergent, then causality is also not fundamental. Causality is the ordering of time, This happened before that, so this caused that. If time emerges from something more primitive, then causality emerges too. And a universe that expands faster than causality can propagate might be operating at a level that is prior to time, where the arrow of cause and effect hasn't yet been established. Here's what this implies for the expansion of the universe. If time is emergent, if causality is emergent, then in the earliest moments after the Big Bang, before the universe had organized enough to give rise to thermodynamic arrows of time and causal structure, there may have been no meaningful causality. The inflationary expansion wasn't outrunning causality. There was no causality to outrun. The universe was in a timeless quantum state, and the expansion was part of the process by which time and causality emerged from that timeless substrate. The universe didn't expand faster than cause and effect. The universe expanded, and cause and effect came along for the ride, like passengers who boarded the train as it was already moving. And right now, as the universe accelerates its expansion again, as dark energy pushes distant galaxies over the causal horizon, we might be watching causality contract, not disappear, but shrink. The observable universe, the causally connected sphere around us, is getting smaller in terms of what our future descendants will be able to see. In 100 billion years, if there are any beings here, their observable universe will be limited to our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller galaxies. Everything else will have been swept over the causal horizon, and those future beings will look up at their sky and see only their local neighborhood, with no evidence that the rest of the universe exists. They'll construct cosmological theories based on that limited view, and they'll be missing almost everything. I want to stop for a second and ask you something genuinely. Pause if you need to. When you think about the fact that your ability to observe the universe is greatest right now, at this particular moment in cosmic history, that future civilizations, if they exist, will be cosmologically impoverished compared to us because they won't be able to see most of the universe, how does that make you feel? Drop it in the comments. I genuinely read them, because the emotional response to these ideas matters as much as the intellectual one, and I want to know what you're feeling right now. Subscribe if you haven't yet, because the next section is going to take everything we've just discussed and apply it to something that's going to fundamentally change how you understand your own consciousness. Because if time is emergent and causality is emergent, then the thing that processes time, the thing that experiences before and after as a continuous stream, your consciousness, might be more tightly connected to these cosmic questions than you ever imagined. In fact, some physicists and neuroscientists believe that the structure of conscious experience might be the reason we perceive a causal universe at all. Let's go there. Everything we've discussed so far has been about galaxies and quantum particles and mathematics and cosmic expansion. Abstract, vast, out there. The neuroscientist Benjamin Libet conducted a series of controversial but deeply important experiments in the 1980s. He asked subjects to flex their wrist whenever they felt like it, and to note, using a fast-moving clock, when they first felt the urge to move. He simultaneously measured the electrical activity in their brains using EEG, and what he found was that a characteristic brain signal called the readiness potential, the electrical buildup preceding voluntary movement, preceded the subject's conscious awareness of wanting to move by up to half a second. The brain was preparing to act before the subject consciously decided to act. Half a second is an eternity in brain time. Half a second is enough time for hundreds of millions of neurons to coordinate. Half a second is enough time for the brain to have committed to a course of action before you, the conscious you, have any experience of deciding. Now, the interpretation of Libet's experiment is still debated. Neuroscientist Daniel Dennett has argued that the experiment reveals something about how consciousness is constructed as a narrative after the fact, rather than being a real-time reporter of neural events. The brain, in this view, tells you a causal story, I decided, therefore I acted, when the actual sequence may be more complex and less cleanly causal. But here's what makes this cosmic. In 1974, Stephen Hawking made a discovery that shook theoretical physics to its core. Using a combination of quantum mechanics and general relativity, not a full theory of quantum gravity, but a sophisticated approximation, he showed that black holes are not truly black. They emit radiation. Thermal radiation, now called Hawking radiation, produced by quantum effects at the event horizon. And because they radiate, they slowly evaporate. A black hole, given enough time, will emit all its mass as Hawking radiation and disappear. Quantum mechanics has a sacred law. Information cannot be destroyed. The quantum state of a system, the full information content of its wave function, cannot be lost. This is called unitarity, and it's one of the foundational pillars of quantum theory. If Hawking's calculation is correct, black holes violate unitarity. They destroy information. Susskind 1. In the 1990s, working with Gerard 't Hooft and Juan Maldacena, he developed a framework that shows information is preserved, encoded in subtle correlations in the Hawking radiation that are individually undetectable but collectively contain everything that ever fell in. The universe is a perfect, lossless information processor, even when it comes to black holes. In 2004, Hawking conceded the bet he had made with Susskind and John Preskill in 1997 and admitted that information is preserved. And those boundaries, those surfaces, are precisely where causality ends. The cosmological event horizon, the black hole event horizon. The surfaces are the places where cause and effect hit their limits. And they are also, if the holographic principle is right, the places where the universe's deepest information is stored. Causality's edges are the universe's memory. Let that sit for a second. The places where cause and effect terminate, the horizons created by faster-than-light expansion, by black holes, by the causal structure of space-time, are not empty. They're full of encoded information, full of the universe's record of everything that ever happened. The limits of causality are also the universe's filing system, which raises a terrifying question that we need to address head-on. If information is encoded at the cosmological horizon, and if that horizon is expanding, if more and more of the universe is being pushed beyond causal reach, then is the universe's information processing capacity effectively decreasing? Is the accelerating expansion making the universe, in some fundamental sense, less complex, less rich? And if so, what does that mean for anything inside it, including life, intelligence, and consciousness? The answer is more disturbing than you probably expect, and it points toward an end of the universe that is stranger and more final than heat death. Let's go to the end. Not the end of the solar system, not the end of the Milky Way. The end. The deepest, coldest, most structurally impoverished future state that physics allows. The place the universe is heading, propelled by the accelerating expansion we've been discussing for the last 90-odd minutes. Physicists describe the fate of the universe in a scenario called the Big Freeze, or sometimes heat death. In the far future, we're talking timescales that make the current age of the universe look like the first millisecond of a human life. The following will happen. Stars will exhaust their fuel. The last star will die approximately 100 trillion years from now. That's 100 followed by 12 zeros. In that darkness, black holes will dominate the universe for an incomprehensibly longer period. But even black holes evaporate via Hawking radiation on timescales of roughly 10 to the 100 years, a googol years for the largest ones. After the last black hole evaporates, the universe will consist of a thin, cold, expanding gas of photons, neutrinos, and other elementary particles, spread across a volume that has expanded to unimaginable size. Now here's the causal catastrophe, and it's the one that connects most directly to our question. Because of dark energy's acceleration, the universe will have essentially no causal connectivity in this deep future. Every particle, every photon, Every remnant will be separated from every other by expansion so fast that no signal can ever cross between them. The universe will consist of trillions upon trillions of causally isolated single particles, each alone in an expanding void, with no causal contact with anything else. The causal web, the network of cause and effect that spans the observable universe today, that connects you to the afterglow of the Big Bang, that makes possible the extraordinary complexity of stars and planets, and life and consciousness will have been completely shredded by expansion. The universe will have reached a state of maximal causal isolation, every point isolated from every other. No causes, no effects, no before, no after. The universe will have, in effect, dissolved causality entirely, not in a dramatic explosion, but in a cold, slow, inexorable expansion that simply separates every cause from every possible effect until causable effect is no longer a meaningful word. This is sometimes described as heat death, the universe reaching maximum entropy. But I want you to understand what that means in informational and causal terms, because heat death sounds clinical and almost peaceful, and what it actually represents is something far more profound. Maximum entropy means minimum information processing. It means the universe has stopped doing things, stopped computing, stopped processing causes into effects. In John Wheeler's framework, it from bit, reality as information processing, maximum entropy is not just the end of complexity. It's the end of reality's capacity to generate new realities. The universe becomes, in the most literal sense, causally sterile. A place where nothing causes anything, where event becomes a meaningless concept, where time, already emergent, already uncertain, has nothing left to emerge from. Does this mean time ends? Technically, time continues in the sense that the universe continues to exist and expand. But time as a meaningful concept, time is the medium in which causes become effects, in which information propagates, in which complexity builds upon complexity, that time ends. The universe becomes timeless, not because it returns to the quantum timeless state of before the Big Bang, but because it has dissipated every source of structure that made time meaningful. And here is the final devastating connection to inflation. The universe began in a state of extremely low entropy, extremely high order, extremely high information density, concentrated in the quantum singularity of the Big Bang. Inflation spread that initial order across cosmic scales, creating the conditions for structure, complexity, causality, time, life, and consciousness to emerge. And now, dark energy is running the inverse process. It's diluting everything, spreading the universe's finite information content across an infinite volume, reducing the information density to zero, restoring, in a sense, the featureless quantum timelessness of the beginning. But on the other side of complexity, the universe began beyond causality. It evolved into causality, and it's heading back beyond causality. We, you and I, right now, are living in the golden middle, the brief cosmic interval when the universe is complex enough for causality to be rich and meaningful, and not yet so diluted that it's been shredded into causal isolation. We are the universe's moment of maximum causal richness. But before we talk about what that means for you personally, and I promise we're going to make this intensely personal in the next section, I need to give you one more scientific revelation, one that flips our intuition about all of this one more time. Because what if the accelerating expansion, the thing that's shredding causality, pushing galaxies over the horizon, heading us toward causal sterility, what if it's not inevitable? What if it's not a fixed property of the universe? What if dark energy changes? What if the expansion doesn't just accelerate? What if it tears space apart entirely? That scenario has a name, and it's called the Big Rip. In 2003, physicist Robert Caldwell at Dartmouth and colleagues published a paper describing a cosmological scenario that made even hardened astrophysicists uncomfortable. The paper was titled Phantom Energy, Dark Energy with W less than -1 and the Big Rip. And what it described was a possible future for the universe that made heat death look warm and cozy. Here's the setup. Dark energy, the mysterious energy driving the accelerating expansion, is characterized by a parameter physicists call W, the ratio of its pressure to its energy density. The simplest form of dark energy, called the cosmological constant, which Einstein introduced and later called his greatest blunder, though he was wrong to regret it, has W equals -1. This gives a constant rate of acceleration. The expansion speeds up, but at a fixed rate. Galaxies cross the causal horizon, but the horizon itself is stable. But what if W is less than -1? What if dark energy isn't just constant, but is actually increasing in density as the universe expands? This sounds paradoxical. How can an energy density increase as space expands? But it's mathematically allowed, and there's no observational evidence definitively ruling it out. Such a form of dark energy is called phantom energy, and its consequences are catastrophic in the most literal sense. If dark energy is phantom energy, the expansion doesn't just accelerate. It accelerates faster and faster without limit. And eventually, the expansion becomes fast enough to overcome not just the gravity holding galaxies together, not just the gravity holding stars together, not just the atomic forces holding molecules together, but every force in nature. One by one, the forces are overwhelmed by expansion. The causal connections they enforce, the local causal fabric holding matter together, are ripped apart. In the final moments before the Big Rip, the sequence goes like this. Galaxy clusters are torn apart roughly 60 million years before the end. Our Milky Way is torn apart 3 months before the end. The solar system disintegrates 30 minutes before the end. Earth explodes 16 minutes before the end. Atoms are torn apart 1 microsecond before the end. And then space-time itself is torn apart in a final singularity. The Big Rip is not just the end of life or civilization. It's the end of every causal relationship in the universe simultaneously. Every atom ripped away from every other atom. Every particle isolated. Every possible causal connection severed in a single universe-wide catastrophe of expansion. Think of it as causality's final defeat. The thing that has been slowly eroding. The causal web connecting you to distant galaxies. The causal web connecting galaxies to each other runs all the way down to the causal connections holding your atoms together. The same process operating at cosmic scales operates at the Big Rip, at atomic scales. The universe's expansion, once just a curiosity about distant galaxies, becomes personal. Now, current observations suggest that W is approximately -1, which would mean no Big Rip. But the uncertainty in those measurements is significant, and the difference between a cosmological constant and phantom energy is difficult to detect with current instruments. The James Webb Space Telescope, launched in 2021, is among the instruments that will provide more precise measurements. The Dark Energy Survey and the upcoming Vera Rubin Observatory will also sharpen our picture of what dark energy actually is. We don't know yet which future is ours. What we know is this: the expansion of the universe is real, it's accelerating, and the only force opposing it is the causal web, the network of gravitational, electromagnetic, and nuclear connections that hold structures together. The universe is in a slow, permanent war between expansion and causality. And in the long run, expansion wins. The only question is how completely. Here's something to think about and drop in the comments. Which future do you find more emotionally confronting? The Big Freeze, where the universe fades into cold, isolated particles over an incomprehensible timescale, or the Big Rip, where every causal connection is dramatically torn apart in a finite time? They're both ends of the universe, but they feel different. Let me know which one hits harder for you. And now, it's time to bring this all the way home, because everything we've talked about, the inflationary beginning beyond causality, the quantum non-locality beneath causality, the emergent nature of time, the deep future end of causality, All of it converges on a question that is not cosmological. It's personal. It's about you right now, in your specific location, at your specific time, with your specific consciousness. Let me tell you something that I think about a lot, and that I don't think gets said enough in science communication. You are not in the universe. You are of it. Every particle in your body was forged in the heart of a star that lived and died before the solar system formed. Every atom of carbon in your DNA was assembled in a supernova explosion, scattered across light years, coalesced into a solar system, gathered into a planet, dissolved into an ocean, organized by chemistry over billions of years, and then organized again by evolution, by culture, by the particular cascade of causes and effects that led to you reading this right now. You are not observing the universe from outside. You are a process the universe is running. You are a local pattern of matter and energy that has organized itself to the point of asking questions about the universe. You are the universe asking questions about itself, and the particular questions you've been sitting with for the last 2 hours. What is causality? What is time? What happens when expansion outpaces cause and effect? These are not academic questions. They're questions the universe is asking through you. You are the universe's instrument of self-inquiry. And here's the thing that should make this feel significant rather than diminishing. Of all the forms the universe could have taken, of all the arrangements of matter and energy that are physically possible, from the vast, causally isolated regions beyond our horizon, to the sterile, particle-scattered heat death of the deep future, conscious life is not guaranteed. Causally connected, informationally rich, thermodynamically organized, quantum coherent, cognitively capable conscious life is extraordinarily rare, even by cosmic standards. The fact that it exists at all, that the particular causal chain that led to you didn't break at any of a million points, is astonishing. The universe didn't have to produce beings who could understand it. It doesn't appear to have any obvious mandate to do so. The laws of physics don't require consciousness. They don't require curiosity. They don't require the capacity to sit down and think about whether causality is fundamental, or whether time is emergent, or whether the expanding universe is tearing the fabric of cause and effect. And yet, here you are, doing exactly that. Physicist Richard Feynman once said something I've thought about almost every day since I first read it. I think it's much more interesting to live not knowing than to have answers which might be wrong. He was describing the scientific mindset, the willingness to sit in uncertainty, to follow evidence, to not need the comfort of premature answers. But I think he was also describing something about the human relationship to the cosmos. We are beings who can tolerate and even be energized by not knowing. We can hold questions that may never be fully answered and find beauty in them. The question we've been sitting with today, what happens if the universe expands faster than cause and effect, has a partial answer. Physics gives us the partial answer. The observable universe, the cosmological event horizon, the accelerating expansion, the deep future causal isolation. But the full answer, what it means for the nature of reality, what it implies about the status of causality in the quantum substrate, what it says about consciousness and time and information, that answer is not yet available. Possibly it will never be fully available because the regions we need to probe are beyond any possible observation. And I want to suggest that this is not a failure. It's the frontier, the boundary of the knowable. And the fact that you can stand at that boundary and look into the unknowable with curiosity rather than fear. That's one of the most extraordinary things about being a conscious being in this universe. You are standing at the edge of what cause and effect can tell us. And you're asking what's beyond. That's not just science. That's one of the most fundamentally human things there is. But I want to push this personal connection one level deeper, because there's a specific implication of everything we've discussed that applies to your everyday experience, not just your cosmic significance, but the specific way you move through your days and make decisions and understand your own life. If causality is emergent rather than fundamental, If time is something the universe constructs, rather than something it exists in, if your conscious experience of a forward-running causal narrative is a construction of your brain rather than a direct perception of physical reality, then what does that mean for the way you understand your own story? I want to talk about free will, not as a philosophical exercise, but as a direct consequence of everything we've explored. If time is emergent, and causality is emergent, and your conscious experience of deciding is a narrative constructed by your brain after the neural events have already begun, then what happens to the concept of freely chosen action? What happens to responsibility? What happens to the felt sense of being the author of your own life? Here's the honest answer, and I think it's more liberating than determinism suggests. The fact that causality is emergent doesn't mean it's not real. The fact that time is constructed doesn't mean it doesn't matter. Temperature is emergent from molecular kinetic energy, but burns still hurt. Consciousness is, in some sense, a construction, but your experiences are genuinely yours. Emergence doesn't negate reality. It relocates it. It tells you that the thing you're experiencing is real at the level it appears, even if it's not a fundamental feature of the universe's deepest substrate. Your experience of deciding, the felt sense of considering options, weighing possibilities, choosing, is real at the level of your life. It has causal consequences. The neural processes that constitute your decision genuinely cause your actions, even if those neural processes are themselves caused by prior states of your brain and body. You are part of the causal web. You are a node in it. Your choices are genuine causes in the universe, propagating forward in time, affecting other nodes in the network. You are a place where causality happens. And this connects to the cosmic picture in a beautiful way. The universe began in a state beyond causality, the timeless quantum state before inflation. Inflation created the conditions for causality to emerge. Causal chains built complexity: stars, planets, chemistry, life, neurons, consciousness. And consciousness is, in the universe's long history, one of the most causally potent structures it has ever produced. A single human mind can initiate causal chains that propagate across generations, through ideas, through culture, through technology, through art. A single human choice, at the right moment, can cascade through history in ways that ultimately affect millions of lives. You are not just a passive recipient of the universe's causal chain. You are an active contributor to it. The causal web that began in the quantum fluctuations of inflation runs through you and is shaped by you. And here's the cosmic stakes version of that. The universe we've established is heading toward causal sterility, toward a state where there are no causes and no effects. The process of causal enrichment, the extraordinary, improbable cascade from quantum fluctuations to conscious minds, is finite. It will end. Every cause that leads to something meaningful is a cause that happens within the window when the universe is causally rich enough to support it. Every moment you spend in wonder about these questions, every moment you spend creating something, understanding something, connecting with another person, contributing to the causal web in ways that matter, is a moment that exists in the universe's brief, precious window of causal richness. That's not a small thing. That is, I would argue, the largest possible framing of what it means to be alive. Here's what will blow your mind, and this is the one I want you to sit with longest. In the deep future, long after the last star dies, and the last black hole evaporates, and the universe is a cold, dark, particle-scattered void, there will be no memory. Not because memory requires a biological brain, but because memory requires causal connection. A memory is a physical state caused by a past event. In the causally sterile deep future, there are no states being caused by past events. There is no memory. Everything that ever happened, every love, every discovery, every moment of wonder, every choice that shaped the course of history, will be not just forgotten, but uncaused by the remaining universe. The universe will not remember that it was ever young, ever rich, ever causally alive. The only record of this universe's causal richness is in the causal richness itself, in the beings it produces while it's still complex enough to produce them, in the minds that understand it while it's still comprehensible, in the art and science and love that get created in the window when the causal web is intact enough to support them. We are the universe's memory of itself. We are the only form in which the universe can know that it existed as a causally rich, complex, wonderful place. That is what you are. That is what's at stake. And that is why understanding these things, sitting with the hard questions, refusing to settle for comfortable ignorance, matters more than it might seem. Before we reach our final section, I want to give you the current state of play. Where are scientists right now with these questions? What experiments are running? What theories are being tested? And what might the next decade reveal? First, dark energy. The biggest mystery in physics is also the most consequential for our question today. We know dark energy exists. The Nobel-winning observations of Perlmutter, Schmidt, and Rees proved it. We know it's causing the universe to accelerate. We don't know what it is. The simplest explanation, Einstein's cosmological constant, fits the data reasonably well, but not perfectly. The Vera Rubin Observatory, which began science operations in 2025, is taking the most detailed survey of galaxy positions and movements ever attempted. By measuring how the universe's expansion has changed over billions of years, it will sharpen our picture of dark energy's nature. Is W exactly -1? Is it varying? Is it phantom energy pointing toward a big rip? These answers are coming within the next decade. Second, cosmic inflation. The BICEP Keck Array telescopes at the South Pole have been searching for decades for a specific signature of inflation in the polarization of the cosmic microwave background, a signal called B-mode polarization caused by gravitational waves generated during the inflationary epoch. If they find it, and the search continues with increasing sensitivity, it would be the closest thing to a direct detection of the inflationary period. It would confirm that the universe underwent that extraordinary faster-than-light expansion in its first moments, and it would give us a window into the energy scale at which it occurred. Third, quantum gravity. The reconciliation of quantum mechanics and general relativity, the synthesis that will finally tell us whether time is truly emergent, whether causality is fundamental, what the quantum substrate of space-time looks like, remains the central unsolved problem of theoretical physics. Approaches include loop quantum gravity, Rovey's framework, string theory, causal set theory, which literally proposes that the fundamental structure of spacetime is a set of causal relationships between events, and holographic approaches based on Maldaceno's discovery. Gravitational wave detectors LIGO, Virgo, and the upcoming LISA space detector are giving us new probes of the most extreme regions of spacetime, where quantum gravity effects might appear. The Event Horizon Telescope, which produced the first image of a black hole in 2019, will continue sharpening our view of the boundary between classical and quantum gravity. Fourth, quantum foundations. The experiments testing Bell's inequalities, the experiments proving that the universe is non-local at the quantum level, are becoming more sophisticated. Physicists are now performing loophole-free Bell tests and exploring the deep structure of quantum entanglement in ways that may reveal more about the relationship between quantum non-locality and the classical causality that emerges from it. The question of why a non-local quantum substrate gives rise to a locally causal classical world remains one of the deepest in foundations of physics. Fifth, the black hole information paradox. The resolution that Susskind and Hawking worked toward, information is preserved in Hawking. Radiation has been strengthened by recent work by physicists Jeffrey Pennington, Ahmed Al-Amhiri, and others who showed in 2019 that you can compute the entropy of Hawking radiation in a way that is consistent with unitarity. This has deep implications for the cosmological horizon case. implications being actively explored by researchers like Raphael Bousseau and Netta Engelhardt. You're not watching a history lesson. You're watching the leading edge of human understanding in real time. We don't yet know what a full understanding of quantum gravity will enable. But every time in history we've asked, what are the fundamental rules? And found them, the results have been revolutionary. Every time. The universe that's tearing its causal web apart at cosmic scales might be teaching us something about causality that eventually gives us power over it at local scales. We don't know. And not knowing, as Feynman said, is where the real adventure lives. Let me take you back to where we started. A black screen. A single white dot. It expanded. And I told you that right now, there are regions of the universe so far away that nothing can ever reach them. Not a rocket, not a radio signal, not light itself. They are moving away from us faster than the speed of light, not by breaking the rules of physics, but by exploiting a loophole. The expansion of space itself that reveals causality to be not a universal absolute, but a feature of connected regions of an expanding cosmos. We've come a long way from that opening. Let me trace the full arc of what we've discovered. We learned that the speed of light is not a speed limit for objects alone, but a speed limit for information, for causation. The universe enforces this not as a suggestion, but as a structural feature of spacetime, encoded in the geometry of the light cone, in the division between the causal past and causal future of every event. And those stretched quantum fluctuations became everything. Every galaxy, every star, every planet, you. We learned that quantum entanglement reveals a universe secretly non-local at its quantum substrate, connected across distances in ways that don't respect the causal light cone structure of spacetime. You can't use this non-locality to send information, but it tells you that underneath the causal surface of classical reality, there is something more deeply connected, something that doesn't respect the rules that causality requires. We learned that time itself may be emergent, a construct arising from the thermodynamic behavior of complex systems, from the correlations between physical clocks and physical observers. The Wheeler-DeWitt equation, the fundamental equation of quantum cosmology, contains no time. At the deepest level, the universe may be timeless. And causality, which requires time, may be timeless at the deepest level too. We learned that the universe is heading toward a future of maximal causal isolation, whether by the gradual heat death of the Big Freeze or the catastrophic Big Rip. The expansion driven by dark energy is progressively severing the causal connections that hold the universe together. Every galaxy disappearing over the cosmological horizon is one more node excised from the causal web. And we learned that we, you and I, conscious beings asking questions about causality at this particular moment in cosmic history, are living in the universe's golden age of causal richness. The window between the causally undifferentiated beginning and the causally sterile end. The brief, extraordinary interval when the causal web is complex enough to support life, intelligence, wonder, and understanding. Now I want to give you the synthesis, the thing that ties all of this together into something you can carry with you. The universe began beyond causality. It evolved into causality, and it's heading back beyond causality. This is not a cycle in the mystical sense. It's a trajectory, a one-time arc from quantum timelessness through causal richness back toward causal sterility. And we are in the middle of it, the most extraordinary middle, when the universe has organized itself sufficiently to be self-aware, when the causal web is rich enough to support minds that can understand the causal web, when the expansion has not yet shredded the connections that make all of this possible. Here is what I find most profound about this, and I want to say it as directly as I can. The universe had no obligation to produce beings who could understand it. The laws of physics don't require consciousness. The expansion of space doesn't require that anyone notice it, wonder about it, ask questions about it. The quantum substrate doesn't require observers. The causal web doesn't require nodes that can map the causal web. None of this was guaranteed. None of this was necessary. And yet, it happened. It happened here. And you are here, in the middle of it, asking the questions. In a universe where causality is not fundamental, where cause and effect are emergent features of a deeper, timeless reality, the fact that you are here asking questions about causality is one of the most extraordinary things that has ever happened. Because the universe didn't have to produce a being capable of asking why. It didn't have to produce a being for whom why is even a meaningful concept. And yet, here you are. You are part of that lineage. Not because you're a professional physicist, but because you just spent 3.5 hours sitting with some of the hardest, most beautiful, most consequential questions that human beings have ever asked. And you stayed. You thought about them. You let them matter to you. That is not a small thing. Here's what I want to leave you with. In 10 to the 100 years, a googol years from now, the last black hole will finish evaporating. The final trickle of Hawking radiation will disperse. The universe will be a cold, dark, expanding void, every particle causally isolated from every other, with no memory, no history, no narrative. There will be no before and after in any meaningful sense. The causal web that stretched from the quantum fluctuations of inflation to the thoughts in your head right now will be completely, permanently severed. And yet, and this is the thing, the fact that any of it happened will not be erased. In the physical sense, the universe's memory will indeed be gone. But in the sense that matters to us, the only sense we have access to, it happened. You happened. Your understanding of the universe happened. Your curiosity happened. Your wonder happened. The specific, real, physically instantiated experience of a human being sitting with the question of what it means for a universe to expand faster than cause and effect, that happened. And it was not nothing. It was the universe being maximally alive. It was causality at its most extraordinary. But here is a different way to think about fine-tuning, one that doesn't invoke design and doesn't require a designer. The universe is not fine-tuned for consciousness, but it happens to be fine-tuned in a way that permits consciousness. And consciousness, once it exists, is the most extraordinary thing the universe can produce, because it is the universe's only way of knowing that it exists at all. Without consciousness, the universe expands, stars form and die, black holes evaporate, heat death approaches, and none of it is ever known. Not by anyone, not ever. It just happens in the dark, unwitnessed. I need to say something about you specifically. Not the general you of a YouTube audience, but you, whoever you are, wherever you're watching from. Possibly the country you dropped in the comments at the beginning of this video, possibly at 2 a.m., possibly on your lunch break, possibly in the middle of a day that felt ordinary until it suddenly didn't. You chose to sit with these questions for 3.5 hours. That's not nothing. That's a commitment to taking reality seriously. That's the scientific spirit expressed as a personal choice. If you haven't subscribed yet, and I'm going to ask one more time, because I genuinely mean it, not just as a channel metric, please do, because this conversation isn't over. The questions we've explored today are alive. The research is ongoing. The James Webb Space Telescope is taking data right now. The Vera Rubin Observatory is surveying the sky right now. Papers on quantum gravity and black hole information and the nature of time are being posted to the arXiv right now. And I'll be here, translating all of it, building on what we've started today, pushing the questions further. Subscribe, hit the bell, share this with someone who you think would let these questions matter to them, and drop your country and your time in the comments if you haven't already. I want to know the full reach of this conversation. I want to know how many places and time zones this question is alive in right now, because every comment you drop is a data point in the most interesting data set I know, the geographic and temporal distribution of people who care about the deep structure of reality. The universe expanded faster than cause and effect. It's doing it right now. It's heading toward a future where causality barely exists. And in the middle of all of that, in this golden, extraordinary, unrepeatable window, you exist. Cause and effect ran for 13.8 billion years and produced you. And you, right now, are using the causal powers of your mind to reach back along that chain and understand it. The expansion can't take that away. The heat death can't erase that it happened. The big rip, if it comes, can't rip apart the fact that consciousness arose in this universe and looked at itself with curiosity rather than fear. You are the universe's answer to the question of whether causal chains can, if given enough time and the right conditions, understand themselves. The answer, because of you right now, in this moment, is yes. Thank you for watching.